Okay, let's go ahead and continue with part 2. And we can start off with the solution of the homework problems. Anyone come up with an answer? 6? All right, we have to come up with a manifold, right? So the space is, do you guys provide drum rolls? No, okay. It's RP3. So that's the answer to the problem, SO3. One way to see that is you can imagine that we just paint the car onto the sphere. Just make a nice painting of a car flat on the sphere. I can put that car in any configuration by just applying a rotation about the center of the Earth, right? That'll put the car in any location, any orientation. So there's a perfect, nice bijection between those, and everything's great. The most commonly guessed wrong answer is S2 cross S1, because it looks like I can pick a point on the sphere, that's S2, and then I can pick a point, I can pick an orientation, that's S1. That would be the case if you can construct SO3 as a Cartesian product of S2 cross S1. You can't. It's actually something more general called a fiber bundle. So it locally looks like a Cartesian product, but when you glue it all together, it's not. Just like I could make a Mobius band kind of look locally like R2, but but when you glue it all together, it's not. There's a twist. So there's a kind of twist across the circles, if you like, when you glue them all together everywhere around S2. If you thought about S2 cross S1, where would the origin be for your third coordinate? In other words, where's the 0 direction that the car should be facing, right? What do you do at the poles, right? There's something kind of wrong with that idea. I believed it was S2 cross S1 for a couple of years until one of my students pointed out that I was wrong. So don't feel bad if you didn't get it. But it does involve this one insight, though, that you can just rotate the Earth about its center, and that will put the car anywhere. Yep. That's what we did before in the first part. That's projective space. So it's the as I said in the last part, the space of rotations SO3 is homeomorphic to RP3, which is real projective space, three-dimensional space. That would be the equivalent to the set of all lines through the origin of R4. So for more details, you have to see I refer you back to the slides of the first part. Any other questions? All right, so that's it. For the latecomers, SO3, that's the answer. All right. So back to the basic motion planning problem. Now we have enough tools so that we can just think abstractly in the configuration space. So this is how the motion planning, the basic path planning problem looks to, let's say, a well-trained motion planning person. There's just some space we're trying to get from one point to another in, and there's some bad parts called COBs. And even though I did initially get descriptions of the obstacles, and I have descriptions of the obstacles, I have a description of the robot, I have everything I need to be able to compute exact descriptions of these boundaries, but it turns out that it's very, very expensive to do that because of the kind of combinatorial explosion you have, because of all the different ways that a vertex of the robot could touch a face of the obstacle, and a vertex of the obstacle could touch the face of the robot, or you could have edge contacts in 3 dimensions. All these cases contribute to a big combinatorial explosion, so that if you want to exactly characterize this, you're in trouble. Furthermore, what if your representations are this polygon soup I talked about? Or if the representation is some kind of point cloud, maybe with some bounding boxes around it, it becomes quite challenging to really even characterize this exactly then. Nevertheless, that's the way we look at things. This outer, the whole space here is the configuration space, and that's partitioned into 2 sets. C-obs, which could be in multiple components, and C-free, which could be in multiple components. And we just like an algorithm where we feed in, not this picture, but we feed in a description of the robot, the obstacles, and what the configuration space is, and the initial and the goal, and the algorithm outputs a path. So that the starting point of the path is here, the ending point of the path is here, and, well, the path needs to be continuous, because I can give a pretty easy discontinuous path that just teleports the robot from the initial to the goal, right? So it has to be a continuous path, so that's where the challenge lies. And note, I parameterize it 0, 1. It does not have to be a time parameterization. So sometimes people call this a motion planning problem, basic motion planning problem. It's also fine to call it the basic path planning problem because it's just a path. you can figure out at what time you should be at which place along the path by reparameterizing it. We don't really care too much when it's a basic path planning problem. So that's our goal. We want to design algorithms that can do that. This is the picture in our heads, but the algorithms only get the description of stuff that's on the first line up there. And we assume that you got the space right in the first place, right? Like these kind of things. So, all right. When we look at existing methods, I'm going to talk about two families, combinatorial planning and sampling-based planning. So this is standard stuff. And as I said, in the afternoon, I'm going to do more of the afternoon's all focused on dynamic environments, and the morning is just motion planning background. So the first part was just the basic spaces that we're reasoning about, how to define the models and all of that, some intro to topology and things like that. Now I'm actually talking about methods for just solving the most basic problem, what was called the piano movers problem. So there are two families of methods. Combinatorial planning, which is also referred to sometimes as exact planning. That was the name that was used heavily in the 1980s. Sampling-based planning, which is also often referred to as probabilistic planning or randomized planning, but there are a significant number of non-randomized versions that work quite fine as well, and sampling-based planning covers kind of a larger envelope then. So that they differ quite a lot in the way that they discretize the problem. So any kind of computation that you do must be discrete, right? You can go all the way back to the Turing machine or whatever you like, but computation is always discrete. Okay, there are some continuous computation models. I have to be careful saying always, but almost always discrete. That's what we normally mean. And so how do they discretize? What is it that they build? What representation that's finite do they end up building? Or possibly countably infinite if they run forever. There's also these things called approximate cell decompositions, which I think might make a comeback, but I won't talk about them, but they kind of use a little bit of both. But otherwise, the taxonomy is fairly sharp, so between these two different philosophies. Here's something we like to talk about in planning a lot. We talk about completeness. So just ordinary completeness, which is the sharpest criterion, is if a solution exists to that problem I just gave you, the algorithm must find one. Otherwise, it must report failure. So it has to tell you yes or no, does a path exist in both directions. It should also report the path, but very often for these kind of questions, people focus on decidability. Does it really decide whether or not there's a path? So complete means yes. Semi-complete is a term that people don't use, but I just put it here because I like it. It's if a solution exists, it finds one. Otherwise, it's allowed to run forever. These first two, if you have background in theory of computation, might remind you of the difference between Turing decidability, right? A decider, an algorithm that decides, versus Turing recognizability. A Turing machine might recognize a language, which means if the string belongs to the language, it terminates. Otherwise, the Turing machine is allowed to loop forever. So it very much parallels that, and that's something we face all the time in planning. The inability to report that there's no solution in a finite amount of time is frustrating, right? We face that with a lot of robotics problems that we try to solve. Resolution complete, very much, it could be a special case of semi-complete, but if there's no solution, it will find one if it exists, right? But if there is not a solution, it can terminate early, and it will tell you there's no solution within some specified resolution, which basically says if there were a solution, I don't know, but if there were a solution, it will have a very small amount of clearance, let's say, right? It would have required a very high precision representation in order to solve it. So that could come back and give you that. There's also probabilistically complete, which is probabilistically complete is probably the weakest of the notions that we have. If a solution exists, the probability that it will be found tends to 1, as the number of iterations tends to infinity. So that would be like a randomized counterpart to semi-complete, if you like. Maybe it could say something about resolution with high probability as well, perhaps. All right, so I'm going to go into combinatorial planning. My book actually goes in the other order. Most people are interested in sampling-based planning, but I think it's important to cover this, and this actually follows chronological order. So these methods mainly came out of the 1980s, and they're heavily influenced by two fields. One of them is computational geometry, and I guess one way to characterize computational geometry, I've heard from computational geometers, is that it's like high-dimensional sorting, right? So So if you want to sort an array, some one-dimensional, just real numbers if you like, they're sorting algorithms. You know it's best to use some kind of tree-like representation, balanced trees and such. Well, what if you have multi-dimensional data? What kind of tree-like representations do you make? Well, one of the first things they proposed were KD trees, for example, that you may know. So it's sorting higher dimensional information is kind of the idea, but it does it in an exact, discrete kind of way that doesn't lose information. They don't make mistakes, which is very nice. And another area which has some overlap with computational geometry, but it's computational real algebraic geometry. I mentioned that in the first part a little bit. And that's because you can formulate all these problems and questions in terms of polynomials and decision problems on the space of polynomials with quantifiers and such. And so that's why people from that field had something to say about motion planning. All the algorithms in this combinatorial planning are complete, so it's the strongest sense. It's the ultimate goal, right? This is the best requirement. We dream of the best possible algorithms. We want them to complete. They usually produce what's called a roadmap in the configuration space, and I'll say that in the free part, in the part where there's no obstacles. I'll say what roadmap means in a bit. They are really nicely efficient and elegant for low-dimensional problems. There's very nice solutions in 2 dimensions. There's good solutions in 3 dimensions sometimes. Some of them extend beyond that even further. But once you get beyond that, they become very difficult to implement. There's also significant complexity issues, which causes a lot of people to just dismiss this entire category out of hand as being something that died in the 1980s, right? But however, there are very useful ideas in here, and I'll try to explain it as I go on, but it's especially the case that if you have a low-dimensional problem, and that's dimension of what? That's the dimension of the configuration space. So if you have a low-dimensional problem, you really should be looking at these methods, because it may be the case that you can do something much, much better than the sampling-based planning algorithms can give you. All right. So here's some idea I want to introduce called a topological graph. So a graph has what? Vertices and edges. Most often when you see a graph, you open up a book on combinatorics, a computer science book, a graph will have vertices and edges and nothing else associated with them, right? I mean, just start with a set of vertices, and the edge is usually defined what? As a relation on the space of vertices, right? So you just have the different edges corresponding to pairs. So this topological graph is one that produces a kind of network of paths in the configuration space. So I mean it to be a graph with some additional interpretation of the vertices and edges. So every vertex is a configuration, and every edge is a path that connects 2 configurations together. So and the configurations that it connects have to be vertices. Is that okay? So that means that whenever I picture a graph, it's both combinatorial, just like it is in computer science typically, but the kind of robotics motion planning version also is some network of paths that their images all become embedded in the free part of the configuration space. So that's something we like to reason about. I just drew some pretty pictures here, but just showing that it can be some kind of graph. I guess those are multi-graphs or whatever you like. You can have self loops. I don't care. But so that's what we have. So I just want to point that out. I'm going to use that. That's sometimes referred to as a one complex if you study topology and such. So one thing I want to say is that sometimes we will work with the closure of the free configuration space. All that means is I include the boundary. So if I talk about the closure of the free space, I just mean I add the points that are on the boundary to it. The reason why that's important is because if you want to solve a problem such as optimal robot planning, like what's the shortest path from one place to another, like if I want to go from here to that projector along the shortest path, turns out I should touch the table. Right? I should scrape the obstacles. If you don't, then there will not be a well-defined shortest path. It's a common problem like you have in optimization when you have a non-compact domain. Right? So that's all. So I just want to point that out. So CL means closure. Just add the boundary to it. But one idea that's very important that came out of this body of research is a roadmap. The topological graph that has 2 properties, and this is very nice. There's a lot of clutter in this particular picture I'm showing. So the roadmap is just the red part. So just kind of focus on the red part. Accessibility. So what that means is I can get to some point on the roadmap trivially. So no matter where I'm at in the free space, like if I'm here, I can get to the roadmap very easily. And this particular roadmap is pretty nice because if you notice, at least some piece of the roadmap is inside of every triangle there, right? So that means that if I want to get to some part on the roadmap, I can move there without hitting anything just by going on a straight line, right? Straight line is like beautiful accessibility. You can get there straight, you don't have to worry about anything. So that's accessibility. And then connectivity preserving is that if I want to go from some initial to some goal, and I want to do it by taking a ride on the roadmap, let's say, right? I'm using the roads to get from one place to another, the red or the roads, then I want it to be the case that if there exists a path from one configuration to another in the space, then there has to also exist a path in the roadmap after I connect to it, right? So just like on the Earth, it may be possible to get from one place to another. Let's see, I was in Iquitos, Peru, for example, I don't know, a few months ago, and there's a big system of roads there, but they don't connect to any other roads on the Earth, it turns out. So you can get there by foot, but if you choose to use the roadmap, it's not going to respect the connectivity, right? You're going to be trapped, and you're not going to be able to get to Iquitos. So too bad if you wanted the Amazon or something. But so it's like the space can get you there, but the roadmap cannot, right? So we want it to be connectivity preserving. This is really, it's like a skeleton that somehow captures the critical structure. And so once people find the roadmap, they consider the problem to be solved. Then you can answer as many path planning questions as you like using the roadmap. That's the idea. One thing that starts to happen in combinatorial planning is that people get very careful about the representations, exactly how to encode the data structures and stuff. And that kind of attention to detail, I would say, people in computational geometry are quite aware of that, and they focus on that quite a bit. They develop data structures that you should use for that. One of them, for example, is called a doubly connected edge list. There's others that are comparable. So, for example, say I just have a two-dimensional problem here. So I have a polygonal obstacle, and these obstacles I guess I can draw which way. So this could be a point robot among polygonal obstacles. But if you're thinking in configuration space already, this could also be what? It could be a polygonal robot among polygonal obstacles, right? Remember that the Minkowski difference that I did last time, so that will just convert it. So we can just imagine that it's already converted, so that we just talk about a point in this space. So I really mean this to be the configuration space. But it causes confusion because it looks like the world for a point robot. So what you typically want to do, if the robot can only translate, I should say, then this is the way it would look. If it can rotate, then this is just what the obstacles look like for one orientation of the robot, and it would change depending on the orientation. Let's suppose it doesn't rotate. Some of the methods I'm going to talk about for this problem also extend nicely to the case where the robot's a disk. In that case, instead of getting polygons here, you'll get your boundary will consist of linear segments and circular arcs. So it's not too bad for that case. So a lot of the stuff, if you have a disk robot like a Roomba, the stuff will work very well for that too. Even if you allow orientation changes, it doesn't matter because a circular robot has circular symmetry. So anyway, so people then like to encode these things very carefully. Like you may want to make a circular edge list for each one of the boundary components. There could be interior holes and such that you might want to run in the opposite direction. So I may make a rule that we go counterclockwise for all the edges of the boundary of the polygon. And then for these other boundaries, we go clockwise. So that when you hit the boundary, the obstacle is always to the left. Isn't that nice? Right? So if you do that consistently, then it makes your algorithm implementations a lot easier. So if any of you, either students or as students, if you've implemented some of these kinds of algorithms, in the first run, people tend to notice that sloppiness really kills you fast. So there's very, very simple things you can do to be clever about your data structures in the beginning, and then you can do the implementation in like 1/10 of the time. It's amazing. So that's the stuff people pay attention to, and usually they keep track of not only that, but every two-dimensional region, they keep a pointer for each edge, which two-dimensional region is to the left of it. And they also make edges going in the other direction and keep the region on that side. And so it's not too hard to build these representations. You can look. There's a number of books that cover these things very well. The particular book by the four Dutch authors on computational geometry, you might find Introduction to Computational Geometry. You might find very, very interesting by De Baer, Overmars, and two others. Let's see. So I won't go into the details of that, but I just want to say that people pay very close attention to the data structures. So I want to give you 4 methods now for solving this problem. I want to solve the, back to this problem again. What was the original problem? How far back was that? This one. But instead of blobs now, it really does look like polygons. And it's not too hard to compute that representation in advance with, again, nice data structures and such. So I'm going to cover 4 methods: trapezoidal decomposition, triangulation, maximum clearance roadmap, or also called retraction method in its original form, and a shortest path roadmap, sometimes referred to as reduced visibility graph. So trapezoidal decomposition. So here's what we do. Take every vertex and try to extend a ray above or below. Sometimes you can't, so if you cannot go below, don't do it. I guess from this vertex you cannot go either way, right? So there's 4 cases. And just do that for all of the vertices, except you stop wherever the vertex hits next. So this is how it looks to make a trapezoidal decomposition. Every vertex I go up and down, and notice what I'm left with is a decomposition of that free space into trapezoids. Is that a trapezoid? Well, it's a degenerate trapezoid that's called a triangle. And these trapezoids always have 2 vertical sides, but one of the vertical sides might degenerate to a point. And then it makes a triangle that's oriented very nicely. So not too hard. There's a very efficient way in O of n log n time to compute this representation, and again, do it all with the nice pointers and everything. I just want to say a little bit about it because it gives the spirit of a lot of these computational geometry algorithms. What you do is you sort the points. I mean, what's my representation? It's going to look like a list of points, right, that represent the obstacles here. So what I do is I sort them by the x-coordinate, and then I sweep across from left to right, just go in increasing order using the x-coordinate. So I start off at the most extreme point up there, and then I take that one, and then I take that one, and then I take that one, and so forth. I go sweeping across, and I try to extend rays up and down. And if you do it in a naive way, you're going to have to test for intersection with all the other edges a bunch of times, right? So that maybe takes what? Quadratic time, right? O of n squared time to do that. But you can do it in n log n time if, when you sweep across, you keep track of the order of the edges vertically. Like you keep track that this edge is below that edge. And then when you go to that one, you keep track that this edge ended and this edge starts. And you just maintain the ordering of those so that every time you do an operation, you can do it in logarithmic time. You can figure out exactly which edge is above and below. And you can maintain all these operations very nicely when you sweep across so that the whole thing is done in n log n time. And furthermore, when you're sweeping across, like when I go from here to this one, I also keep track of the fact that I can move from this cell to this one and this one. So I keep some pointers. I start building a graph. This is going to be our roadmap. And we just build that up very nicely. So we end up with a roadmap like this, where I decided to put a point, which is a vertex, in the interior of each one of the cells, and of the 2-dimensional cells, I should say. And I also put a vertex in the center of each one of the 1-dimensional cells, which are just vertical bars here, right? I decided to pick the centroids for all of these, which it's arbitrary, but centroids look nice, so I did that. If you do that and then you connect the dots based on adjacency, then you end up with a nice roadmap representation. If I want to solve a planning problem now, say I want to get from here to here, I just figure out which cell I'm in. That's called a point location query in computational geometry, so you can study that as well if you do more study of these kinds of methods. So that's not too hard to do. And then we already have they're all sorted by x-coordinates anyway, so you could keep that pretty easily. All the points are. So we just connect to the centers of the 2-dimensional cells, and then we just do graph search, right? Use whatever you want. We don't have to do things optimally. You can just use breadth first search. It doesn't matter. If there exists a path in that graph, then you connect the corresponding dots to make the path, right? If there does not exist a path, you can conclude with 100% certainty that there is not a path that solves that problem. Okay? So very nice. Very clean. And the neat thing is that all of these cells are convex. And what's the basic definition of convexity? The definition of convexity is motion planning is trivial. Right? No, not really. The definition of convexity is what? For any pair of points, when I look at the line that connects them, right? I stay inside the set. That's motion planning is trivial, right? You just connect by straight lines. So it's perfect. So that's why you see convex cells coming up all the time in these kind of algorithms. You can also deal with non-convex ones, but the further from convex you get, the more cleverness is required to be careful. You don't want to accidentally stab into the obstacles. All right. Now, there's nothing special about this particular method, and nothing special necessarily about making trapezoids. Why don't I just do a triangulation? So I could do this. Just take every vertex and try to connect it to some other vertex that's visible, that I can actually connect without hitting something in the interior, and just keep doing that and doing that and doing that. And there's nice theorems that say that it will converge to producing a triangulation. You could do it in kind of a horribly naive way, and again becomes inefficient. However, there exists, actually it's quite amazing, there exists an algorithm that can triangulate a simple polygon. This one I guess not a simple, but it's triangulate a simple polygon in linear time, but it's quite complicated to implement. I don't think anyone ever has. But it was an algorithm by Chazelle in like 1983, I think, linear time triangulation. It was covered in the New York Times, but it was such an amazing result in computational geometry, but it's still not implementable by humans. So it's kind of interesting. So there's a lot of study going on, and like what's the fastest running time you can possibly get in theory versus usable, implementable stuff. I recommend just look in standard computational geometry books, and you can find n log n time triangulation algorithms. These are for simple polygons here, but it's not too hard, and the complexity does not go up much for polygons and poles. So I recommend that it's worth reading into that if you want to do triangulations and you have I don't know, 1 million edges or something. All right, let's see. So then we just build an easy roadmap again by just putting a vertex in the center of each cell and then connecting adjacent cells. We put a vertex in the center of each 2-cell and each 1-cell, 2-dimensional cell, 1-dimensional cell, and then connect it all together. And we can use that very easily again because we have convex cells. So quite fine. Well, let's suppose we want to have a roadmap with some nicer properties. So here's an idea, the maximum clearance roadmap. So whenever the robot, let's say, is here, this is the closest obstacle. Whenever the robot up here, that's the closest obstacle. Whenever it's at the midpoint here, if these are parallel edges, then all along there, the two obstacles are equidistant, right? So if you've seen Voronoi diagrams in the plane for a collection of points, which is always telling like which is the nearest point, so it gives you regions that tell which is the nearest point, then this is a generalization of that. You replace the points with obstacles. By Odin, Lang, and Yap back in 1983, the method was introduced that, in fact, this is probably the first, I would say, roadmap algorithm that came into motion planning. And essentially what you do is you can imagine gradually thinning these corridors until all that's left is a skeleton. That's called a deformation retract in topology, and you can formally look at it that way, but the algorithm itself doesn't precisely compute a deformation retract, but that's the idea. So it looks something like this. This would be a maximum clearance roadmap. So if you want to keep away from the obstacles as much as possible, assuming you wanted to go down to this area anyway, the best you can do is to get onto this, right? This point here, the vertices correspond to places of triple equidistance. And there are 3 obstacles or more, if it's degenerate, that are closest to you at those places. The curves along here, notice you get curves, which is interesting. The reason why is because the roadmap itself, the idea of closest is based on features. A feature may be an edge or a vertex. So if the closest features are edges, then this is the part of the maximum clearance roadmap. If the features are vertices, for example, if that's a triangle here and it's a triangle here, that's the closest point. But you might remember in one of the kind of nice geometric definitions of a parabola, if you have an edge and a vertex, or a line and a vertex, you get a parabolic curve. That's the set of points for which the point and the line are equidistant, right? So that makes second-degree arcs in here. And if you do it naively, you can just try all combinations of edges and vertices and get all the curves and then compute their intersections. Makes a nice class project to torture students with, maybe. But it turns out it can be done, and then that would be into the 4th time algorithm to do that, trying all the combinations. But you can do it, the algorithms that have been presented all the way down to O of n log n time and implementation. It's actually very hard to even draw these, so I stole this one from Laton's motion planning book. I think it's hard to even guess what the curves are going to look like unless you actually implement the algorithm, right? Because it's tricky stuff. Anyway, it's quite interesting. It's quite nice. So if your goal is to maximize clearance, to keep the robot as far away from the walls, this is a nice one to use. Now let's try to get as close as possible to the walls. What if I'm really in a hurry and I want the shortest path possible? Well, for that, we have the shortest path roadmap. So in that case, optimal motion planning is easy in polygonal environments. It gets a lot harder in higher dimensions. I'll mention that in a bit, a little more. This is the roadmap that will do shortest path planning for you. And one way to imagine this roadmap here is, what if I have a string and I try to pull it tight, starting at some initial configuration and some goal configuration, and maybe I wrap it around some nails and I try to pull it very tight, and I ask you the question, first of all, what vertices would it get stuck on, right? Like, for example, if I put two nails here and here and I pulled tight, it would get stuck on this, right? If I was up here in the top, like in the upper right corner, the upper left corner, it would get stuck at that vertex right there. So the vertices that it would get stuck at are the vertices of the shortest path roadmap. And what are the edges? The edges they get stuck at are something called bitangents, which I will talk about in a bit here. But again, same kind of idea. And notice there's these edges here, but it's kind of hard to see, but we also include edges along the obstacles, because it's possible if I start here and pull tight a string, I would get stuck on this part here, right? So, so those are included. The vertices are what we call reflex vertices. If the interior angle, notice for all of these vertices, if the angle here into the interior is greater than 180 degrees, then it's added. Because it's poking in, right? So any vertices that poke into C3 have to be added, because the shortest path might get stuck on them, right? Those are the places where you would have to graze the obstacle, like the corner of the table example I gave a little while ago. And then the other cases are bitangents, and what this means is that it's cases where I have to draw a segment between, let's say, P2 and P5 here, if and only if it's possible to extend rays just a little bit. All you need is a small epsilon, but if you can extend rays just a little bit beyond P2 and a little bit beyond P5 before it hits something else, then you have to put something here. Because if I got, let's say, right here with one nail and right here with another nail, and I pulled a string tight, the string would get caught exactly along this curve, right? And so that's why these cases are in here. It turns out if you like to do numerically robust computation for these algorithms, which I advise, you can do it, you can calculate these without even doing any trigonometry or anything like that by just implementing a predicate called left turn predicate. It takes 3 points, and it's true if those 3 points make a left turn. Like, for example, if I go P1, P2, P3, I made a left turn. If I go P3, P2, P1, I made a right turn, so that's not left turn. So you can make a left turn predicate. You can do that by just putting these coordinates, add an extra 1 to them, put them into a 3x3 matrix, and look at the determinant. And just based on the sign of the determinant, it will tell you whether or not it's a left turn. So it's a very nice, numerically clean way to test for left turns and right turns. And then this thing's a bitangent if and only if this condition holds. It's this left turn exclusive or that left turn, or this left turn exclusive or that left turn. So you just got to kind of look at the cases. I won't go through all of it, but this one, P1, P2, P5. So if P1, P2, P5 is a left turn, exclusive or P3, P2, P5 is a left turn, and so forth. So if they're both left, then that doesn't satisfy it, right? You got to make that statement true. Work out the details if you want, but it will give you a nice left turn test. The only reason why I put that in my book too, and I did that because I went through some years of headache with horrible numerically unstable implementations of these algorithms, and then finally coded it like that, and it was just clean and beautiful and never gave me problems. So just that stuff really is important. It doesn't look like it on paper, and it doesn't look like it in people's research papers, but if you want to implement these things, subtleties like that really go a long way. All right. So now if I want to solve a problem, here's my query, right? I want to get from the initial to the goal. So I just try to connect to whatever vertices I can reach by a straight line. that are on my roadmap. So I try to connect to these up here, and I connect to these here. And then I just do a graph search. And that's it, to find a path. Can I use any graph search? Well, we have to have optimal paths here. So to find any path, I could use any graph search, but algorithm, like breadth first search if you want. But you want the shortest path here, so maybe you want to use Dijkstra's algorithm or A star if you want to get a little bit fancier. And just find, and of course the edge weights are just the lengths of the edges. And then that will find the shortest path for you. Right? And in order to solve this problem, note the shortest path has to touch the vertices, as I said. So that's the example where we're using the closure of the configuration space. So for optimal problems, everybody in control theory likes to do optimal stuff, right? Just be aware that in planning, we tend to resist optimal solutions a little bit. We tend to like feasible solutions only, and ones that maybe are far from obstacles might be better for us. So it's all, you got to be careful what you're optimizing. Maybe you might say, oh, it's optimal clearance then, but that's a second criteria, and now you're stuck trading off the two criteria of distance versus clearance. Maybe you want to look at Pareto optima. I don't know. That's the kind of problem you have. But anyway, oh yeah, that's what the solution looks like. All right, so let's look at higher dimensions. So what happens when we go up a bit? If the C-space is 3 or more dimensions, most methods do not extend very well. So optimal path planning for 3 dimensions, just among polyhedra, is already NP hard. However, it can be approximated very easily, not only in polynomial time, but there's very efficient algorithms for making approximate optimal solutions. I can show you some value iteration kinds of computations, for example, in the afternoon that do that very well. But if you want exact answers, it's dead, because you can't just simply connect vertices, because in 3D, optimal paths might just go across the interior of an edge, and you don't know where exactly along that edge, so there's no easy way to extract it. Maximum clearance roadmaps, well, they become disconnected in 3D. You have to add more pieces, it gets more difficult. But the trapezoidal decomposition method, it turns out, extends beautifully. You just get kind of 3-dimensional boxes. And you just recursively apply the method to each dimension, and it's really, really nice. So that's one method that does extend. So if you have polyhedra in 3 dimensions, or for some reason you may have piecewise linear representations in n dimensions, this is a nice method, actually. If you don't go crazy trying to maintain data structures that are higher than 3 dimensions. I mean, that's another issue, but it's really clean, nice algorithms for that. When we get up to higher dimensions, I got to make sure I have time. I want to get through all the sampling-based planning as well, and I want to say a little bit about differential constraints too, because that'll be useful in the afternoon. When we get into higher dimensions, we tend to have either specialized decompositions, like for one particular problem, people have solved it very nicely, or we have very, very general methods. But the general methods ultimately can't efficiently solve every problem, because the motion planning problem is p-space hard. That was shown by John Rife in 1979. That implies NP hard. So, so if you don't know what p-space hard means, NP hard is fine. If you don't know what that means, let's just say hard. Right? But people know how to do it, but you're probably not going to find an efficient algorithm to solve it. Actually, the exponential part that people believe about these classes, exponential in dimension, is not even the trouble. These algorithms also have trouble because of the high degree of polynomials as well. There's a whole bunch of problems. But even if you want to rearrange a bunch of rectangles, say these rectangles are translation only, and I want to put them from one configuration to another, but I let the number of rectangles be unbounded. Like I can give to your algorithm as input any number of rectangles. That problem is p-space hard. So I don't need to have high-dimensional nonlinear transformations, all kinds of crazy things going on. Even just rearranging a bunch of rectangles is p-space hard. Now, if I fix the number of rectangles in advance, if I tell you you're never going to have more than 5 trillion rectangles, then a polynomial time algorithm exists. There's no problem, right? So, because you've made the number of dimensions a constant. So you got to be careful. They're playing little tricks on you sometimes with these complexity things. It's important to pay attention to that. All right. As I said, there's specialized algorithms. I just want to say something about that, and then I'll say a little bit about cylindrical algebraic decomposition, a little bit about Canny, but very, very brief, just to give the flavor. So for example, maybe you have a line segment robot that moves around in the plane. So it can translate and rotate. So what people have figured out, Schwartz and Scherer, and I think a guy named Bagnon implemented this back in like ICRA 1990 or something as an implementation of this, where They computed three-dimensional cells in the configuration space. This is just a projection of what they look like, so you can kind of see their boundaries. Kind of hard to see, but like in this cell, there's one cell where the rod's going this way, and there's another cell where the rod's going this way. And so there's actually a stack of cells for each region I show you here. So it's a three-dimensional collection of cells, and they figured out all the adjacencies, beautiful stuff. So it's not bad. They figured out exactly a nice cell decomposition for that. More generally, they borrowed ideas from computational real algebraic geometry, something called Collins decomposition, which implements what's called a cylindrical algebraic decomposition. I won't go into the details of that, but the number of cells that it produces is doubly exponential. So what does that mean? Kind of like O of 2 to the 2 to the n, but it's not even as nice as that because it's not 2 to the 2, it's some other nastier stuff. So it's worse than that. But the precise complexity is in my book if you like, but it's high. That was actually a grand open challenge of the 80s from about 1983 to 1987 was, can it be done in singly exponential time? The answer was yes. Canny's thesis, it won the outstanding dissertation award of ACM, the Association for Computing Machinery back at the time. This was the main result. And it produces a roadmap directly by doing, some kind of ideas, let's say, that combine computational real algebraic geometry with Morse theory, if you know some of these things. But brilliant algorithm, and there's still mathematicians that continue to improve the bounds on it and such. And if you like to understand these things, you can see this book on algorithms in real algebraic geometry, which covers Canny's algorithm, cylindrical algebraic decomposition, in hundreds and hundreds of pages of precise mathematical detail. And you can get everything there that you might ever imagine. It's very interesting. And if that's not enough, you can look at Sugata Basu's page, for example. It has papers on more recent generalizations. They moved beyond semi-algebraic representations and moved up to what are called O-minimal structures. So it's a generalization that goes beyond polynomials and such. So a lot of interest in that. So basically, it looks like mathematicians only that mainly care about these algorithms, sadly. But it was nice back in the day because these were very deep, open theoretical questions in robotics. To my knowledge, I don't think anyone's ever implemented Canny's algorithm. So it's interesting, right? Best thesis of all of computer science in the year of 1987, but I think there still may be no implementations of it. I heard of a guy in Japan doing it once, but I'm not sure if he finished. So I have to, it's like that. Very, very few people. So I think the algorithm may actually be useful for some real problems, but everyone's afraid. It's very few people understand it. So anyway, all right. And these guys who wrote the book, they're not going to implement it, I'm sure. They like proving theorems. So. All right. So across the 80s, that's kind of a snapshot of the way it looked, and that caused a lot of people to believe motion planning is dead. What are you going to do? These algorithms, the best you can do looks really intimidating and really inefficient. Well, that motivated people to weaken their requirements a little bit and go into sampling-based motion planning. I could make an analogy. It would sort of be like, how many optimization problems can you solve analytically? And then after you give up, what do you do, right? Or how many integration problems? I want to integrate some function. How often does it work out to have a nice integral, right? You integrate it, works out nicely, or do you have some horrible error function or other kinds of elliptic integrals and things like that don't work out, right? So if they don't work out nicely, what do? Well, you do sampling, right? There's sampling-based optimization, sampling-based integration, Monte Carlo integration, for example, quadrature formulas and such. So same thing happened to motion planning. We got sampling-based. So the idea is we put a layer of separation now. We hide all of the nastiness of how the obstacles and robot are interfering. We put that inside of a black box called collision detection so that the algorithms or the designer of the algorithm now can be naive about how all of that stuff is done. Can be kind of naive about it. Which is interesting because in the 80s, everyone who did motion planning really thought carefully about all these constraints. Now we have kind of a culture of people who don't think about them too much, right? Which is unfortunate because I think you can really improve a lot of the algorithms by thinking carefully about them again. All right, so the collision detector separates it out, and we try to somehow systematically sample the space that we have. And the methods generally divide into single query and multiple query. Query is what? Like question. How many initial goal pairs do I want to solve, right? I want to get from here to here, and then here to here, and then here to here. That's multiple query. Single query is just one shot. For a given problem, I just need one problem solved and I'm done. All right. I think the most fundamental idea of mathematical concept for sampling-based planning is denseness. So what is denseness? So this can be defined entirely using topology, so just topological spaces. So a set U is called dense in V if the closure, remember the closure, we're just adding the boundary points. If the closure of U is equal to V. So what does that mean? So one implication of that is that every open subset of V will contain at least one point that's in U. Here's a very nice example. Take the rational numbers, right? The rationals, what is that? That's the set of all fractions, right? And all the ordinary fractions, just some integer divided by some integer. Take the set of all those. You know that you can get arbitrarily close to any real number with a fraction, right? Usually the numerator and denominator might get bigger and bigger as you get closer, but you can get arbitrarily close with a fraction. So the rational numbers are dense in the real numbers. So no matter what open set, if I pick any open set of real numbers, there's going to be fractions inside of there, right? Everybody buy that, hopefully? Right, so that's all. That's one way to see denseness. This is just a generalization of that. Remember that all of the spaces we talked about in the morning, we view them as subsets of Rn. So if we view them as subsets of Rn, whenever I talk about a dense set, it's going to mean that there's no open ball that has not been touched, right? So every open ball is going to contain some samples in it. That's going to be the denseness idea that we care about. Another thing that happens is, even if you've seen dense sets somewhere before, fewer people think of them as a sequence. So I can take a set that's countable and give an ordering to it, right? A countable set, right? A finite set I can order, right? Here's the first element, second element, 100th element. If it's infinite, maybe it's uncountably infinite, in which case I can't do anything. But if it's countably infinite, then I can sort the elements, right? I can assign a natural number to each one of them. So that's what this is doing. Right? So I'm going to assign a natural number to each one of my samples. That produces a linear ordering, and I will call that a dense sequence. Here's something kind of neat, and this is convenient, and why a lot of these algorithms work well, is that a random sequence, if I could really generate a purely random sequence, it will be dense with probability 1. Right? Imagine I start throwing darts at the real number line, and I get to do this forever. Is there going to be any interval on the real number line that's been missed? Right? The answer is probably not. With probability 1, nothing will be missed. Right? So that's a very nice property of randomness. But you don't need randomness to get that. You can even do it deterministically and not even have to mention probability. So what do we do? I want to start sampling spaces to do sampling-based motion planning. I want to sample the configuration space, right? The space of all transformations is what I cared about. So what most people end up doing is using random sequences because almost every programming language has a random function, right? So why not use it? Easy. And if I sample the x-coordinate randomly and sample the y-coordinate randomly, looks like I get a random xy point, right? If I want to sample theta randomly, fine, stick that on. So it's very easy. I can just combine, samples. Everything looks nice. Still, you might want to think of them as pseudo-random sequences because they're actually generated according to some specific formulas, and the formulas were started by some seeds. So they're actually deterministic in some way, but we pretend they're random because they satisfied some nice tests. One thing to be careful about, I think is kind of interesting, is in these sampling-based planning algorithms I'll talk about, we often end up having to sample over some curved space. Of course, the famous one is this one, as you now know as SO3, right? So if I sample over SO3, if I want to generate a random sample, let's think about SO3, what does it mean to have a uniformly generated random rotation? Right? It's kind of a strange idea, I think, right? If I put a random point in a disk, I think you all know what that means, right? It's like, well, all right, the probability that this part of the disk is hit, some area of the disk is hit, should be the same as the probability that some other part of the disk is hit, as long as those two parts have the same area, right? So this is where that Haar measure idea came in. If you want to sample SO3, what you should do is generate a point on S3, that high-dimensional sphere, at random on the sphere. If you do that, you will respect the Haar measure. You will actually have a random rotation, which is very nice. That means you have no bias towards any particular rotation. I think it's pretty cool. Another neat thing, this is a clever trick that goes back to Arvo and Shoemake. It's out of graphics gems. People in graphics know. It's a very, very neat trick. I don't have time to go into the details of it, but everyone should know it. And that is that if I just pick 3 numbers uniformly at random, U1, U2, U3, this beautiful simple formula will give you a random point on the 4-dimensional sphere. It will give you a random rotation like that. That's amazing. So if you're ever generating random rotations for SO3, just do this. It's beautiful. So just everyone should know that. It's really nice. If you try to do something like that 1 dimension lower or 1 dimension higher, it won't work. It just works exactly for this dimension. It's an amazing hack. Well, hack, I don't know. There's a theorem that says that it works too. So it's a really clever. All right. Now, we don't need to do things randomly. Here's a great idea. This goes back to a Dutch mathematician around 1930 or so, named Van de Corput. I really like this. Let's start counting in binary, and let's try to count off numbers between 0 and 1. And let's just suppose I'm going to count 16 numbers. I'm going to go in 1/16, counting in binary. So that's what I do down here, okay? And now, if I look at that, what's happening? The points going from 0 to 1 just stream across, right? They go from left to right, streaming across. If I were to be stopped early, say I only got through half my points and then I collapsed, I don't know. So then all my points would be on one side of the space, right? What I would like is a sequence of points so that if I stop it at any point, it looks pretty uniform. So Van de Corput had this beautiful idea of just reversing the order of the bits. So now what did I do here? I just flipped the bits, right? Or I could have taken these decimal points and stuck them on the other side and then read, say, the Arabic way, right? So that'd be fine. But we don't do that. I just reverse the bits for you here. And now I look at what sequence I get. Isn't that interesting? So first it hits in the, First I hit the endpoints. I decided to identify. I can do the identify trick. This is actually points on a circle. So that point and that point's the same. I don't want to deal with the ends. So that's the first point. Then I pick one in the middle. Then I go to that one and that one. Now look how it dances around very nicely. It's always jumping around to different parts of the space so that if I stop it early, I get nice uniform coverage. That's just like what random numbers seem to do, right? They dance around very nicely. But this is actually more uniform than random. I'll say that again, more uniform than random. If I put down a bunch of points at random and you did some tests, if you noticed, if I went and did like bucket tests, I put down a bunch of points at random in the plane here, and I do bucket tests. If all my buckets have the exact same number of points, something fishy is going on, right? Because random points should put a few too many in some buckets and not enough in some others, right? Otherwise you won't pass something like a chi-square test, which is kind of what I'm applying. Well, so it turns out that in order to be random, you have to be a little bit far away from uniform. So we call it uniform random, but it'll be very low probability to have a truly uniform distribution. So Van de Corput beats this easily, and it's a very nice, strongly uniform sequence. And it turns out I didn't have to stop this at 1/16. I could just keep on counting. All I have to do is just extend more bits here and just keep going. And it'll do 1/32 and 1/64 and so forth, and it continues onward beautifully. That's a great idea. So people want to generalize that to higher dimensions, and they have in all kinds of literature and such. So here's an important idea, dispersion. And the idea is, what's the radius of the largest empty ball? So dispersion of a set of points. So if I put a bunch of points down, that's like the pepper spots here, then what's the radius of the largest empty ball? Here, using an L2 metric, you can use whatever metric you like. This is the largest ball. It's a disk here in the plane. If I use an L infinity metric, then my balls become cubes, which is still a ball to a topologist, right? So who cares? And that's the largest cube. I guess my example is not too good. Cube could have been somewhere else because you changed the metric. If my space is bounded, notice that a dense sequence always drives the dispersion down to 0, right? Because like I said, you can't put an empty ball anywhere. You can't put an open ball that's empty anywhere if you have a dense sequence. So it will always drive the dispersion to 0. All right. Well, that's nice. It turns out the Van de Corput sequence is asymptotically optimal in terms of dispersion. You can actually do a little bit better if you care about the constants. Oh, that would have been a nice homework problem. No, anyway, it's really simple construction, but it's amazing. You can do a little better. you can generalize it to multiple coordinates. It's just instead of using binary, like for the x coordinate I use binary, for the y coordinate I use base 3, for the z coordinate I use base 5, and so forth. You have to use relatively prime bases, otherwise it will not produce a uniform sequence. So it's a little number theory involved in there and such. But when you do that, that's called a Halton sequence. And as I said, it's better than random. This is how much, this is a factor of non-uniformity that uniform random numbers are compared to these kinds of sequences. So, and if you notice, this is some factor, okay, log n over n, but you need that many times as many samples to produce the same dispersion. But notice that as the dimension gets higher, the factor doesn't matter too much. So unless you have a lot of points. So in very high dimensions, random, deterministic, use whatever you want, but when you get down into lower dimensions, even in dimensions 5 or 6 or something, you may notice a significant difference. If you want to learn all about these methods, there's a beautiful book by Harold Niederreiter on that, if you like. It influenced me a lot in thinking about sampling-based motion planning. So here's something interesting. It's from that book, actually. I call it the Sukharov theorem. So this came from a Soviet mathematician around 1971, I think. He was interested in the problem of optimization. So I want to solve optimality problems, and I have, say I want to optimize some function. I have Lipschitz constants that bound how fast the function can change. So how should I sample the space to report an approximately optimal solution efficiently? Well, it turns out that the best you can do in placing samples, if this is all assumed over a unit cube, this is a two-dimensional example here, then the best you can do is just to tile the space with little cubes and put a point in the center of each cube. If you want to optimize the dispersion, you can do no better than that. I found that really fascinating because I think at that time in motion planning about 10 years ago, there was a lot of belief that randomization was overcoming the barriers of cursive dimensionality. And here's an old Russian math paper that says that grids are the best you can do, right? And at that time, everybody believed that grids are the worst you can do, right? At least a lot of people seem to believe that, and so I thought that was really interesting. So it turns out grids are the best you can do. The dispersion here is L infinity, so that means the cubes become boxes. If you want L2, then you have what's called the sphere packing problem, and you don't want to deal with that, trust me. We don't want to go that way. But the same kind of results apply up to a constant, but figuring out what that constant is, nobody wants to, well, some people like doing for a living, let's say. It's hard stuff. So all this really says is that the dispersion is going to be no better than, dispersion says what? If I want to put an empty ball in here, I got to fit it in between these, I want to look at how far away could I possibly get from the points. It's going to be no further than this amount, right? And this, k to the 1 over d is just the number of points per axis. So what's neat about that is if that's the best you can do, that means that no matter what I do, random, deterministic, all of these fancy tricks, I cannot drive the dispersion down any faster than a grid could have. I think that's very interesting. All right, so, here's one thing that's very interesting. This is kind of a detour. I think everyone should know about the Johnson-Lindenstrauss lemma, so it's just one of my favorite things. Like some lemmas, it never gets promoted to a theorem. I'm not really sure why. It's very important. Like Fatou's lemma gets used all the time in real analysis, for example. I don't know. I guess once a lemma, always a lemma. I don't know what. It basically says that you might not need as many dimensions as you thought you needed, which is kind of a cool idea. So if I pick some epsilon and some set of points in Rn, there exists a projection, maps it from Rn to Rm, so that for any pair of points I pick, if I apply my projection, the distance does not get distorted any more than 1 minus epsilon and 1 plus epsilon. So in other words, my points don't get distorted by very much, so I might as well just jump to the lower dimensional space. And it turns out, and it has nothing to do, it's amazing, right? There's no other conditions on the points or anything. I just have k points in Rn, and there exists this mapping, and m is logarithmic in n, and it's related to epsilon, right? So of course, the higher quality you want, the more you're going to pay for it in dimensions. But what's interesting about it is that you seem to only need logarithmically many dimensions, which I think is really amazing, right? That's the basis of methods in machine learning that reduce dimensionality. It's the basis of compressed sensing, right? You may have seen compressed sensing around, especially if you have a signal processing, electrical engineering background. And I think it's at the core of those subjects. That's one of the kind of the core results. I think it should be also at the core of motion planning. I don't always see it, but it should be. So also, it's used quite a bit in computational geometry as well. So that's how I learned it from computational geometers, and I see it more and more. So anyway, that was a little detour to that. In other words, maybe you don't need all those dimensions anyway. You should think about it carefully. All right. So we can kind of think of a spectrum of sampling sequences. I want to generate a dense sequence. Could be random, pseudo-random, some low dispersion sequence. There's cleverly designed ones, or even a multi-resolution grid. They're all kind of comparable in some sense. I just want to point that out. All right. Like I said, so the intuition is that irregularity is not really helping you. So all of those will kind of perform the same way, really, for these different kinds of methods that I will present. All right. Let's say a little bit about collision detection. Let's see, about a half hour left for this part, and I'm going to get a little compressed. Let's see. Okay. I think I was going okay, but I added the differential constraint stuff, and I want to make sure I can get that in. All right, let's see. So for collision detection, I'll just say a little bit. We typically, it's used as a black box, but if you want to know a little bit about the internals, people usually make hierarchical representations of the obstacles and the robots. And mostly are using collision detection packages, most of which come from the University of North Carolina, from Menosha and Lynn's group. So many of us have been using those for years. One thing about it is that there are incremental methods which can very nicely keep track of the closest pair of features between the robot and the obstacle, so that if the robot moves a little bit, the amount of computation you have to do is just a little bit, which is very nice. So that's incremental, rather than just from scratch answering the question, are the robot and obstacles in collision? It's very important to pay attention to that. If you just use a black box collision checker and it's not incremental, you may pay a performance hit of maybe a factor of 10 times or something, and for no good reason, right? So just a little more cleverness, you may get much better performance by using incremental collision checking. So just something to pay attention to. Also, one problem we always have, we sweep under the rug a lot in these algorithms that I'll talk about, is if I want to connect together Q and Q prime, how many points in between should I check, right? If my collision checker can only guarantee that a single point is collision free, I guess I have to call it an infinite number of times, right? To validate an entire edge. Nobody wants to do that, so they do it some number of times. If you still want to guarantee that it's collision free, then you could use workspace distance information that's reported by some collision detection algorithms. And you can use that information and then use essentially what are Lipschitz bounds. In other words, if I perturb the robot by a small amount, it makes me louder, if I perturb the robot by a small amount by rotation, you can bound the maximum amount that it could move in the workspace, right? So that will give you a way to prescribe exactly how much to chop up the space to guarantee that you're being collision free. So those are some little details. I'm going to talk about one kind of general framework. I call it incremental sampling and searching. We have some kind of graph that we start off with. Usually it includes the initial and the goal and nothing else. But maybe sometimes it may have other things in it. We have two methods that we specify. This is like a template of a method. We select a vertex, and then we do some kind of local planning method to taking that vertex into account to generate possibly a new edge and new vertex in the graph. We may also have a step here where we check for solution. We should have that step so that we know when we're done. If we're not, we keep iterating. And these algorithms might run forever. They tend to be semi-complete, as I said. That's our goal usually when we design these. It's very nice to think about the difficulty of motion planning problems in sampling-based motion planning in terms of bug traps. It's a very convenient way to express the challenges that we have. So, for example, if I want to get from the initial to goal here, if you want to apply A-star search in a 27-dimensional space or something, you'll get stuck in this potential well here and you have some kind of trouble. But for most existing modern motion planning algorithms, this is a very easy kind of problem to solve if this is the obstacle region in the configuration space. If you have a problem where there's a bug trap, like maybe you were stuck here and I just grew one kind of tree, right? I grew one roadmap or tree, I think I called them a topological graph. I grow one topological graph here, and it may be really hard to find this opening, but maybe from the other direction, it's very easy to move along the surface somehow, depending on what kind of local planning method we have. It may be easier to go in one direction than the other. This happens a lot in motion planning, it's like easier to go through a funnel than it is to find the top of a volcano and then go into it somehow. So it's just the way things tend to work a lot. So that tends to make us use bidirectional methods where we're growing the graph from the initial and the goal. Maybe you need more than that because maybe it's easy to get into these regions but hard to get out of them. And maybe it's just really hard no matter what you do. You know? So these are the different ways that we try to tend to look at these problems. This is very early, very effective pathfinding algorithm. I thought it was really impressive when I was a student. I saw this around 1992 or so when Latone came and visited University of Illinois when I was there. So this could solve, I think, up to about 30-dimensional problems, right at about the time when everybody thought motion planning was dead. You know? So it was really amazing. And you can think very much like, what if I want to do A-star search or best first search? And so I start going for the goal, but then when I get stuck, what do? I can detect that I'm stuck, and then I do a random walk for a while, and then I try again. So I got stuck, I random walk, maybe I fail again, I random walk, maybe I get lucky and get out here, get stuck again, random walk for a while, and then eventually I get there. So it was amazing the difficulty of problems that it solved, but it unfortunately required a lot of parameter tuning. It's called a potential field planner, so it's closely related to the ideas of potential fields of Khatib, but this is done in configuration space, so and done for planning with obstacles. And of course, it has local minima problems, and it's very difficult to design the parameters so that you get it to solve problems over and over again. So it's a very unpredictable kind of planner, but when it worked, it was impressive, right? So then we spent a lot of time, maybe a decade or so, trying to make algorithms that run reliably and with less and less parameters. Or if there is a parameter, we really need to understand what the motivation is for that parameter. So that's the direction we went after that. So here's another kind of method. Maybe I just put a low resolution grid, right, very small like the Sukarev-like grid, and then I connect these edges together, and then I just connect to it like it's a roadmap, and then go from place to place like that and do a search. So that's one possibility. I can just validate the edges while I'm searching. Here's some other incremental planners. I won't have time to talk about those. I'll talk about the third one, the RRTs, as you might expect. But a lot of interesting planners here. I think the Alrand's clue algorithm is a precursor to the RRT that influenced my thinking a little bit because it's trying to aggressively explore more space, and that's something I always thought was kind of important. I think Karpin and Pilanetto's adaptive random walk planner is interesting because it's so incredibly simple. It just generates one long random walk, but tunes the step sizes during execution, and does remarkably well, which I think is really, really interesting. Right? So sometimes simplicity really goes a long way. All right. So anyway, back when I was thinking about, I really wanted to make some kind of trees. This is an interesting experiment. Suppose I have a square. I didn't put the square yet. I have a square region, and I want to explore it from the center. And let's suppose that I start off at the center, and I just put in an edge at random in some random direction. And then I pick one of the two vertices at random and add another edge to that at random. And then I pick one of the three vertices at random and add an edge to that in a random direction. What will it do? Will it kind of randomly cover the space? Here's what it does. Isn't that weird? So if I just keep randomly picking a point in this graph and then randomly, adding a vertex that goes off in a random direction, it will just make a horrible mass in the center. So that's actually not at all uniform. It's heavily biased towards going inward, let's say, rather than outward. So early on, I kind of thought I want to pull it out. I want to stretch the tree out. And so the insight that I had around I guess the summer of '98 or so was I imagine that there are all these advisors kind of popping up saying, "You should pull the tree towards me," right? I'm part of the space here, and I'm not represented. So you find the nearest vertex in the tree, and then try to extend it towards that advisor who's saying, drive towards me. Go a little bit. In the early versions, I always went a little bit, and then another advisor pops up somewhere else saying, pull the tree towards me. So the space itself is pulling on the tree. You're not even focused on the query at this point. You're just trying to fill the space in an aggressive way. So that was kind of the intuition that led to that. So that's the idea. You just pick a configuration, say at random in the space, find the nearest vertex, and then add an edge to your tree that tries to go all the way to the vertex or maybe just goes a part of the way. If you want to solve a planning problem, you could just, instead of picking a random configuration, maybe every 100 iterations you could just pick the goal, and then we'll bias the tree towards there. The goal bias tree works sort of okay. Another thing you can do is you can replace the random configuration here with any dense sequence. I don't care. So it can be deterministic. That'll make rapidly exploring dense trees, which could be random or not. And if you use the deterministic version, then you also can get resolution completeness, right? You can also say, okay, I know that with certainty, I've covered the space down to some level of resolution. So that's very nice. A little bit of implementation issues on RRTs. Well, we select the nearest vertex using the metric to the random point. But if there's an obstacle, then we only. Oh yeah, I should say this first of all. Sorry. When we extend, if you're just using the RRT for ordinary path planning, then we extend all the way to the random point or whatever the deterministic point was, and connect it by a straight line, whatever the shortest path is in the configuration space. If there's an obstacle, then we just stop short. That's all. So it doesn't matter. So we still might generate samples that are inside of the obstacle region. We do not waste time on that. One thing that's very helpful is that if you have long edges in the RRT, you should actually connect to the nearest point on the tree, which might be in the interior of an edge. So that's actually much better, and that's how the tree looks for that kind of case. And I highly recommend doing that. Now, then you need to do edge point tests. You have to find the nearest interior point along an edge. That's a little bit of a computational geometry problem by itself, which you might want to solve. If you don't want to solve it, what most people do in hacking is they just stick a few intermediate vertices along the way to make sure none of the edges are too long. So anyways, a couple of implementation details that we don't talk about them too much, but they may affect the performance by a factor of 10 or something pretty easily. Also, it's good to use KD trees for nearest neighbors because this method is doing nearest neighbor queries all over the place. This will dramatically improve performance once you get past a couple thousand nodes. So if you want to solve a problem, then you do a bidirectional search. I already gave you the example of a goal bias tree. If you want to go 2 trees, just start one from the initial, one from the goal, and in step 1, we just grow the initial tree in the standard way. But then in step 2, we take the new vertex of the initial tree, and we pretend that's the random sample for the goal tree. And then we reverse the roles. We extend the goal tree using a random sample, or again, whatever the deterministic one is, if you like. And then we try to extend the initial tree using the new vertex that we added for the original tree. And that will very easily for you solve some number of problems. It doesn't solve everything, but people have found it useful for a number of problems and such. So this is just a simple 3-dimensional configuration space problem where we grew a tree from the initial and goal and then projected down. You cannot see the orientation dimension here, but we just grow a tree and connect them together. All right. Are there any questions so far? So I'm getting down near the end here. Got to make sure we have time for the homework problem. So, single query versus multiple query. Well, if you're going to have a lot of queries, then it may make sense to pre-compute something, right? Everyone knows this in computational geometry and all over in algorithms, that it very often pays off to pre-compute a data structure and then do fast queries over it that relies on the investment that you did a priori, right? So it's very natural for motion planning to think this way. This sort of template is based on the probabilistic roadmap framework that Kavraki, Latome, Overmars, and Shvestka came up with around 1994 or so. So the idea is, in the most basic form, is just generate a bunch of points at random in the space. You have some radius parameter here, and then you want to connect to other points within the radius to build a kind of graph. And if you don't do anything more than that, you'll end up with a gigantic graph that might not be too helpful. So there are a lot of particular sampling methods that try to make it more efficient and such. The most basic ones, you can use k nearest points, you can do connected component analysis, you can try to vary the radius, maybe as the number of points grows, which, by the way, there's a very nice paper by Karaman and Frizzoli in IGRR 2011 that uses percolation theory to tell you exactly what the radius should be so that with probability 1 you end up with a connected structure in the end. I'll also refer to that work a little bit later in the afternoon, but it's very interesting stuff. And percolation theory was started by Hammersley, who also worked extensively on theory of low discrepancy sequences and sampling, and so it all has this kind of a common history and such, so very interesting stuff. Also visibility, that may be another way to do it, and that will be one extension I will talk about. This is a method developed at LAS in Toulouse, and the idea is we have visibility, which basically means what is the set of all points from that configuration that I could connect to by a straight line in the configuration space. And now what I want to do is I have only two kinds of vertices that I decide to keep in my probabilistic roadmap or sampling-based roadmap. If I want to make a guard, there's guards and connectors. If I want to make a guard, then I must make it so that no guard can see another guard. And then I have connectors, and their job is to connect multiple guards. So if they can see two or more guards, then they're allowed to exist. No other vertices can exist, and that has the effect of dramatically pruning the number of edges and vertices you put into your probabilistic roadmap. And then it has very nice convergence guarantees. So the kind of skeleton you get out, you have to do a little more work to make this one, but it really produces a very nice small structure. So that's I'd say one of my favorite variants of these probabilistic roadmaps. All right, differential constraints. So I have a little bit of time for that, and then we go on to the homework problem. Well, thanks to robot kinematics and dynamics, we all know this, we face this all the time in robotics. The systems are locally constrained, right? A robot has wheels, let's say, then it can't move the wheels sideways, right? There's friction, it has to go in the direction that the wheels are rolling. If I have mechanics, like let's say momentum, right? I have constraints due to that, so I can't just go in any direction I want locally. People in computer science, especially in the time when they were developing a lot of these fundamental pathfinding algorithms, don't care too much about differential equations, right? So they're happy to abstract that away. And the mentality was to leave the differential constraints for those control theory types who like to worry about it, right? But if you leave it to the control theorist, you may have made a mess for the control theorist to worry about, because you might not have produced even a good path for the control theorist. Or maybe they would prefer for you to give them a vector field to work with or something else. So it's very important to consider differential constraints directly in planning. One way to do it is just to say, well, we'll still compute a path, but it'll be a time parameterized path and one that satisfies differential equations. So that's the idea. So we could say that up to now, maybe all I did was allow any direction. So I could say, well, my q dot, I mean that to be the time derivative of configuration. So dq dt is equal to u, where u is just any velocity vector I like. Okay, to make it easy, let's just bound it. So any velocity vector up to unit magnitude. So in other words, I could go any direction I wanted in these spaces and it didn't matter. So that would be the kind of differential constraint we've solved up to now, the trivial one. So now let's make it a little harder. Well, let's say, well, maybe I have a control system. I have q dot, again, that's dq dt as a function of q and u. And I have some usually bounded set of controls that I apply to it. Now I finally start to care about time. By the way, in the afternoon, when I do the dynamic environments part, we're going to be talking about time a lot, as you might imagine. So we have some function that's now time parameterized. I have a time interval, 0 to tf, final time. And the configuration at time t is given by an integral, right? We don't always evaluate these integrals in some analytic way. We may do numerical integration and such to figure out what's actually going on. But we're integrating this f function, the system, forward from some initial configuration. This tells us the velocities that are allowed. This is just q dot. And that's how we figure out where we're going to be. So the whole process now of figuring out where you're going to go involves applying some u function into f and integrating to figure out where you're going to get. So it's an extra, it sounds like we need another black box now, right, to figure out where we're going to go. That's the problem that control theorists face all the time. So a very simple example, one of my favorite examples goes back to Dubin's car. Lester Dubin came up with this around the 1950s or so. I think Lester Dubin's mostly worked on statistics, if I'm not mistaken, but this is kind of an odd paper that he came up with once. Really interesting. He didn't call his own thing a car, I think, but these are just curvature-constrained shortest paths. And so that's what he worked on. But anyway, the car got named after him. So imagine I have a car that can drive forward only. It can stop if you want. And so there's a maximum amount that the wheels can turn. So that means that when it does the tightest turn possible, it follows a circular arc. So that's some kind of constraint, right? I cannot just take the car here and just move this point sideways, right? So that's a differential constraint. Here's what the x dot equals, or sorry, q dot equals f of qu looks like, the control system that I gave before. Oh, I wrote it right there. Okay, that's what it looks like in this form. So that's what it looks like. And so that differentially constrains the car so that if I start trying different inputs or actions or u's that I can apply to this, it might look like this after 2 steps. I can do a hard left, hard right, or go straight, and then do it again. This is how it might look after 4 steps. So it starts to get complicated now to reason about where we might end up. Of course, I could have tried maybe some, if I'm allowed to, I could have tried some angles in between, depending on the model and the problem. The next thing that happens is that if you want dynamics, notice that these constraints came out only because the wheels have to continue rolling and don't slip. That's how we picked up differential constraints there. Those are kinematic differential constraints, but when we get into dynamics, you have to move, well, you don't have to, but you should probably move into the phase space. When we get up to the phase space, then we have higher order derivatives on the configuration variables, so we move to a higher dimensional space most of the time, but not always. We just take the state space here, called state space X, and we have a now 2n dimensional space where we have the first n components are q, my configuration variables. The next n are my velocity in configuration space variables. So that then I make a control system of this form where this x dot now, that's the time derivative of these guys, so that actually has q dot and q double dot in it, which is enough now to say the velocity and acceleration is some function of configuration and velocity and whatever my action or input was. So that's what we get up to now, standard control system representation. One thing that's important to think about is when you get into the configuration space, when you get into the phase space now, there's this kind of cylindrical structure. We have the obstacle region in the configuration space. That's the set of transformations that causes collision. Now, any possible velocities don't really matter here, right? It doesn't matter how fast you're moving. All that matters is that you're touching the obstacles. So that's a region you should avoid. So now we have the collision region in the phase space or state space. This is just a function that converts states into configurations. That's all. So I didn't define that. One thing that's kind of interesting is when we develop planning methods in this context, we can actually do resolution complete planning in an interesting way by just taking the set of inputs and quantizing them, taking the time interval and quantizing it, and then we can vary the amount, the level of quantization that we do for time using smaller and smaller time intervals. And then in this iteration, we just do breadth first search, and I can make a third axis here. So this axis is just number of iterations, let's say a breadth first search, just trying different combinations of actions. I can make a third axis, which also is different discretizations of the actions, if you like. And then, because all of this is countable, I can just run around and explore this whole space, eventually growing out and covering all possibilities. And there's some more work you need to do to show that it's resolution complete. But it's actually, you can make very simple planners that are resolution complete. The question is, how efficient is it in the end in finding solutions that you care about? So I should say that when we do these problems now, we have a local planning method. This is where we do the numerical integration usually. It can be solved analytically for some problems, great. We do numerical integration. This is an easy problem, usually for us. It's not always, you know. You could have a horrible, complicated vehicle dynamic simulator or some other kind of thing. System simulation is not always easy, but for most of our robotics problems it is. But this one's significantly harder, which is if I want to connect from state, let's say xi to state xg, I want to know which action will do it parameterized over time, what control will do that. That may be quite hard. So I just want to point out that for the regular motion planning problem, this was trivial, right? I just connect the dots, right? I just drew straight line segments. Now this becomes a hard problem. So that's something we always have to worry about now in planning under differential constraints. So I might prefer to just go to a goal region instead of a goal point. Then I don't have to worry about the boundary value problem of getting to some precise point here. If I do have to connect precisely to some point, then it's unavoidable if I grow a single tree now from the initial state, then I have to I have to deal with the boundary value problem somewhere if I want to precisely get there, right? So I just want to point that out. There's like a mini control problem or a mini planning problem inside of the big problem, no matter what you do, unless you just want to connect to a goal region. So if you want to grow backwards from the goal, you're going to face the problem in the beginning. If you want to do bidirectional search, you might face boundary value problems all over the place trying to connect trees together. If you want to make a roadmap, like a probabilistic roadmap, you might then have to solve 1,000 boundary value problems. You probably don't want to do that. So that's just something. Actually, was my thinking originally with regard to the RRT was that I wanted a kind of space-filling tree that did not have to solve boundary value problems all over the place. So if I were to just immediately make a roadmap, like the probabilistic roadmap, I would have to solve a lot of boundary value problems. But for planning with differential constraints, which was my original thinking for the RRT, for something like this, it will never have to solve a boundary value problem. All right, so here's a couple of methods quickly, and then the homework problem. So here's a couple of methods. This is a really nice method by Barakhan and Latome, which basically just, they apply it to a car-like robots, like Dubin's car, and another one that can go in reverse called Reed-Ship car. I think there's a car pulling a trailer in the paper, too. I think that was a popular extension at the time. What you basically do is you grow forward, making this kind of search tree by just applying different actions and keep the time step fixed. Look at the places where you go, but then you bucketize, let's say, the space. There should be a third dimension here for this example. So you have cubes, and you make sure there's no more than one vertex inside of each cube. So if you ever arrive to another cube a different way, you just throw it away. Right? And so by this, they fill the space nicely. There's also ways to do this where you gradually increase the resolution so that you can be resolution optimal. There's ways to do that as well. But anyway, I think it's a very nice method. And under some conditions, you can prove that you have approximately optimal solutions coming out in terms of shortest possible path. Or maybe minimizing the number of reversals is another thing people like. If you want to apply RRTs or some of the other incremental sampling and searching methods to planning with differential constraints, you just have to apply whatever control inputs you want. There's a much more difficult problem here of designing good metrics and designing good motion primitives, which I don't have time for. But that becomes a big issue under differential constraints, and there's still a lot of research on that, I would say. Emilio Frazzoli did some interesting work early on in his PhD thesis in 2000 using the RRTs and designed very good primitives and cost-to-go metrics for autonomous helicopter flight in real time, in simulation, but he had a real-time planner with moving obstacles and such. It's very impressive. And so if you cleverly design these, you can do well. But the point is that you don't try to connect to the random sample. You just apply some inputs or actions to the system and integrate forward for a while and pick whichever one gets you closer and you're fine. It does not pay to spend a lot of time optimizing there. You do not have to do the boundary value solution there. All right, so that's the end of this. I'm going to still get my homework problem, but combinatorial versus sampling based, those are the big types of methods. Pay attention that for some problems, combinatorial methods are far superior. And the understanding that went into those could, I think, in modern times improve our sampling-based algorithms quite a bit. I think that, in robotics, if you've applied out, if you've seen motion planning algorithms applied to anything, in robotics or outside of robotics, chances are with sampling-based algorithms. Because of that, because of the way those work, we tolerate these weaker notions of completeness. And remember that we always kind of confront dimensionality somewhere, but it's not really randomization that's helping because of the Sukarev grid thing that I talked about. Sometimes you can use deterministic alternatives, but be careful as you use them, but they may provide good performance that's at least as good or even better than random, and they provide deterministic guarantees, which might be handy. If you want more on the things I've talked about, there's chapters 5 and 6 of my book. And finally, the homework problem that you can do over the lunch break. So this is about dense sequences. All right, so I first want to give a little notation. So let's say alpha sub k is the first k sequences, first k points or samples of some infinite sequence. So this is an infinite sequence we talked about. And this one's a little bit, well, you have much longer now. You have lunch, right? It's 2 hours. So this one you have to cook up a space, but my hint is don't make it too complicated. The answer is really, really easy. Some of the simplest things you come up with might work. So it's nothing really, really weird. So I want you to find a metric space, X. It's one of these nice ones that we embed in Rn, everything's fine, and a sample sequence so that the dispersion, remember dispersion is what? That's the radius of the largest empty ball, right? So if I have a finite number of points in my space, what's the biggest ball I can put there? The radius is the radius of that ball is going to be the answer for dispersion. If the ball is unbounded, then the dispersion is infinity. All right. So what I want is a sequence for which the dispersion is infinity for all k. So no matter how many finite set of points I use, I keep adding more and more points, the dispersion is always infinity. But when I use the whole sequence, bam, it becomes 0. Right? So that's weird. It's kind of like a sequence that's infinity all the time, but in the not very good kind of limits, it becomes 0. So can you find just some kind of simple space and some kind of nice way to sample it? There's a lot of different ways to do it with regard to samples, but very, very simple things will make this happen. So that's what I'd like you to think about. Remember that alpha k is just any finite subsequence of that, starting from 1, will have infinite dispersion. But when I use the whole thing, it goes to 0. That's it. So I'd like you to think about that, find a nice example of that. And then we will come back for part 3 at 2:15, all right? All right, thanks very much.